Hello, I'm Neem, and today we're going to make some trees. Yes, lots of people have made videos about trees and Minecraft, and yes, we can make Minecraft trees better. That has clearly been established already. But can we make them any more accurate? And will they look any good? Using a thing called tree architecture and a touch of Da Vinci knowledge, we will design some Minecraft trees based on some very loose science and maths. I say loose, that's entirely because I'm the one imparting this information here. The point really is to see if we can design some trees or plants using some standard models of plant growth that already exist in the professional world. We will be remaking all the existing trees loosely according to their architectural models. We start with the azalea, and then we have the acacia, followed by the birch, the two types of oak, spruce, the jungle trees, and finally the mangroves. These blocks up the side indicate approximately the biggest one of this type found in nature, and the block on the side indicates the approximate average heights IRL in case you wanted to do some scale stuff. We see the mango trees can actually get up to 60 meters. That's massive, right? The jungle trees on average get to about 25 to 40 meters, with the tallest one in Brazil around 80 meters. Then we have the spruces that get to 70 to 90 meters at their tallest, but they average from 20 to 60 meters. So you see we're going to the top of this pole. When I used to climb trees and something was really, really tall, you'd get to the top and chuck something off and see how many seconds it took to get to the bottom. So let's do some science right now. Whee! So these heights are really just to give you an idea of how trees would be in relation to each other in nature. I haven't really stuck to them. I explain that a bit later, and I'll do more in other videos. And by that, I mean I've gone for mostly average heights to show the relationships between them without needing to be 100 blocks away. So both oaks, the dark oak and the light oak, get to around 40 meters, averaging around 20, with the dark oak definitely being the bigger of the two. The birch, the tallest one's around 35 meters, averaging again around 20 meters. They form woodlands with oak trees, so I guess that would make sense that canopy height is averagely the same. Acacias, we're looking at around 12 meters. And the azaleas are clocking in around 6 meters. But before we build any trees, let's first deal with some basic nomenclature, or the terms that I'll be using. I mean, you probably know a lot of this, but it helps for referencing. So you've got the stem or the trunk, and for this video, when I refer to the first order of branching, I'm talking about the stem. The branches, big or small, will be the second to fifth order branches, and then we have the growing tip or apical bud. There are many buds all over the tree. Well, most trees, palms only have one, and they open to produce leaves, flowers, and the beginnings of new stems. But for the purpose of this, we care about the one that is steering, leading from the top, the apically dominant bud. And that is now replaced with arrows showing the direction of growth in these two growth models. Monopodial, you see the bud at the top is leading the way, the leading bud. We call this apical dominance. With monopodial growth, the leading bud remains dominant over the lateral branches. Now, some trees stay like this for most of their lives, but a lot of trees start like this and lose their hierarchy when they get older, meaning they become more spready and less like Christmas trees. The example given is of a mass type model, and our spruce trees fit into this model. With sympodial growth, the apically dominant bud bends over, becoming a side branch, and a new side branch becomes the leader. This repeats as the tree grows. This is sympodial growth. You can see this in the troll model, and you'll find that some acacia fit this model. I think that's about all we need for now. Leonardo da Vinci had a rule called the tree rule. Da Vinci wrote, all the branches of a tree at every stage of its height when put together are equal in thickness to the trunk. In other words, if a tree's branches were folded upwards and squeezed together, the tree would look like one big trunk with the same thickness from top to bottom. When a stem or branch forks, the new order of branches will be equal to the mother. So assuming that our first order branch has a value of 1, then our two daughter branches that come from it would be 0.7 in real life, but for the sake of block game, let's say 0.5. So if our stem is 1 block wide and it splits in two, each second order branch would be half a block wide. Each third would be a quarter. So let's also say if our stem is 1 block in width, we could then place half-sized blocks such as walls as secondary branches and posts as third order branches to represent the size change. For this reason, I chose to use walls, posts and blocks for this project. This is the ratio I'll keep in mind as I build these trees. I want to keep some scale, but I don't want to make giant trees the size of mountains. For example, if we use Grove 3D in Blender to generate a birch tree and add a remesh, change it to blocks, we can see the scale needed to get the angle in game is massive. We will make it though one day. So we have an understanding of what blocks we're going to use and their relationships. But not all trees grow the same, so how do we decide about branch placement about the stem for different types of tree? A tree architecture gives us models or blueprints for groups of plants. It focuses on fixed and repetitive phenomena in plant structures, allowing us to identify the building plans of the plant. Plants can be grouped according to characteristics. These are elongation of the axes, growth habit, growth direction symmetry, and flowering, terminal or lateral. So we can match a tree to a model, but these models are 2D. So how does this 2D pattern translate to a 3D tree, or more specifically, a Minecraft tree? If we research the tree we want to remake, we can see the way the branches grow on the stem. This may be tricky to do with just Google searches, but the information is there, you just have to dig around a little. Or you can go out and look at one yourself. Arboretums are amazing places to see lots of different trees in one place. If you're in the UK, Westernborough Arboretum is our national arboretum, and it's fantastic. So you see here, I'm just comparing the gaps between the rhythmic branches and then looking at the branch location and number and how they grow out of the stem. If we compare our image search with our model, this should give us something to go on, so we know our spruce is massa and the branches grow all the way around. Mostly, we kind of get this shape. So assuming we have 4 sides that a branch can grow from, we can grow from diagonals, but because to get a good attachment for the branches you would need to attach to a face or faces anyway, I'm ignoring that option for now. And after going through a few tree types, I realized that I could maybe use 4 patterns to cover most of the branch types we would need for our trees. I also decided I could make my own rule for interpreting models into 3D branching in Minecraft, because why not? So first we ask, is it rhythmic? If yes, we ask if the branches grow all the way around the stem. If no, do they grow opposite each other in pairs or groups? If we got a no for the first question, we ask if the branch placement is random or spiraled up the stem. All of these answers lead to a pattern to use when making new trees. These patterns are A, rhythmic branches all the way around. B, rhythmic branches opposite or in pairs or groups. C, continuous spiraled. D, continuous random. So let's go make some trees putting together the stuff we have just covered. starting with azalea, which is a type of rhododendron and can be found natively in America or Asia. These generally follow the Leuenberg model. The tree is sympodial with rhythmic branching. It kind of forks and forks and forks again. I chose pattern A, I think, for this one. The terminal bud becomes a flower, and then the lateral buds take over each time. I'm going to be honest and say most of the ones I've ever seen look like this. They're usually shrubs, but there are some arboreal or tree ones. So acacias are from Africa and Australasia. Growth of the branches is modular and sympodial. As you see, it grows up and then over, up and then over. We're looking at the troll model. It's sympodial with continuous branch growth. Pattern C or D will be fine. I've gone mostly D. And the reason they have flat tops is to do with light exposure. In the northern and southern hemisphere, the sun will hit the tree at different angles. In some places, it's just not worth having branches and leaves though down and maximizing the leaves exposed to the sun. As a result, the same trees may look slightly different in the northern hemisphere to how they do in the southern hemisphere. And the yellow glass I've put up represents the yellow flowers called mimosa flowers that you'll find all over this tree. I had to take one down once that was really in the wrong position and I almost cried. It was so beautiful. Another thing I want to mention with the acacia, but this applies to other trees too. We've talked about why they may have a flat top, but often they're flat along the bottom as well, as if someone has gone along with a hedge cutter. Well, this is often caused by browsing animals such as cow, or deer, or giraffe, or elephants, or humans that think trees should look like that. So I flattened the top out a bit more and did some browsing damage at the bottom, and it should look a bit more authentic now. The birch is a deciduous broadleaf tree found throughout the northern hemisphere. Deciduous basically means the leaves fall off in winter or severe conditions. Birch follows a continuous version of Rau's model. It's probably easier to picture Atim's model, though I stress the tree doesn't actually follow this model in real life. Birch is sympodial with continuous branching that's upwards tapering. Pattern D would be good, but pattern C will work fine. This birch at the back is what a lot of forest birch trees kind of look like at the top. Their lower branch is gone because there's not much light that gets past the woodland roof of leaves. This is also what it might look like if you pruned the apical bud at any point or got damaged by squizzles or frost or lightning, whereas the one at the front you could find in an open space like a park or garden or a glade. See, trees in open space will grow differently to forest trees. The oaks. I've treated this as two subgroups of the same tree essentially. I'm going to take some liberty here and say that the straight up oak trees represent the faster growing oak tree species like red oak from North America maybe, with the dark oak as a slower growing oak like European or American white oak, which generally have longer lifespans and darker timber. They are mostly deciduous temperate trees, but there are some evergreen oaks like holly oak which do exist. And most oaks I checked are in the Rau model, but for the most part, like the birch, they follow a non-symmetrical version of the Rau. You could use a model like Atim's to get the shape if you wanted to, but I have based mine off some newer models, that plus many years climbing and measuring oaks. I've gone with patterns C and D for most of the branching for both oak and dark oak. I made versions of all the models displayed. These models are ideally for Quercus robur, but although the growth habit of Quercus rubra or the red oak is different, I think these models should suffice for both tree types. The light oak doesn't get as big in height or spread, is not as dense and not as long lived as the dark oak. And with the dark oak, I added some things for some realism to get a little biodiversity. You see, trees are ecosystems like mini cities. Bugs and fungus live in the dead wood, which feeds the birds and the squizzles and the other beasties. And the mushrooms here, which are really just reproductive organs for fungus. The fungus is actually made up of mycelium, hyphae, and those fruiting bodies, and forms relationships with the tree's roots called mycorrhizae. Basically, the roots and the fungi join together to help both parties uptake nutrients and water more efficiently in a mutualistic way. This friendly fungus can also help stop other fungus eating the tree. Some people even say that this network can be used by the tree alongside pheromones to communicate. And then we have lichen. Lichen doesn't just grow in caves, it grows on walls, trees, and just about anything that doesn't move. Some tree lichens are very special in that they only grow on bark that is hundreds of years old. And did you know that lichen is not one thing but a symbiotic relationship between a fungus and an algae? That's pretty dope, right? Spruce trees. A spruce tree is a type of conifer. Spruce trees, for the most part, at least the ones I've researched, follow the Massart model. They're monopodial and rhythmic. So pattern A, the first one is pretty standard player-made minecraf tree. It's just a pyramid, right? So, hey, you can make it as big as you want. Just remember, in an open place like a park or a field, the branches would come right down to the ground level or browsing level if you have animals about. This next spruce with the pom-pom bit at the top is what you get when trees are older and packed together in a woodland. The light doesn't get down to the ground, so there's no need to have the lower branches, right? Also, some species of conifer lose their lower branches to prevent fire spreading up the tree, like sequoia. And with the tree at the back, I imagined that the top had snapped out in a storm to give you an idea of some variation you could make to indicate age and damage. This picture inspired me a lot. I did also think about making some pine trees, but decided not to in the end. If you want to make some pine trees, you could research the row candelabra shape, and that would work for quite a lot of pines. Jungle trees. To be fair here, you could take any of the models previously made or shown and stick them on a big stem like the conifers, and using a mix of leaf types and wood types because jungles are so diverse. Temperate forests generally only have 1, 2 or 3 species with understory plants like an oak ash woodland in England or monkey puzzle forests in Argentina. But jungles are a bit different, with individuals of the same species spread sometimes kilometres from each other. There are many reasons for this: spread of pathogens among species, prevention of monocultures, and so much more. Man, enough to fill a whole video and some. So this first jungle tree, I used a Leuenberg model and really emphasised the buttresses on the bottom of the tree, adding some climbing epiphytes such as vines or tree flowers. Variation is the key here, and mixing up size and shape. On this last tree, it's pretty brutal actually. I imagined a creeper fig. So these grow up over the trees, using them as a frame before engulfing them, with the host usually dying and rotting away with just the creeper fig standing left as a tree. I also wanted to do something with the cocopods and theobroma, or chocolate, and this follows Nozeran's model. They are perfect understory plants for jungles, and it just seems right that the chocolate is on a small understory plant and not on the big tree, And finally we have the mangrove trees. Mangroves are native to many parts of the world, with the ones in West Africa reaching 60 metres, though averaging about 10 to 20 metres. They are also vital to the health of coastal areas the world over. They for the most part follow the Atim's model. They seem mostly monopodial regarding main stem growth, and from what I can make out they have mostly continuous branching. So I use pattern D mostly. I'm guessing the minecraf mangroves are red mangroves, as they have the longest stilty roots, or rhizophores, and are red-wooded. They generally live out in the water a bit rather than on the shore. I made white, black and red mangroves because they change species as you move closer inland. We can then look at the roots and their knees for more variation. If we use this pick as a guide, I put the white ones on the shore with the light branches, not too many stilty roots, and lots of knees. The black ones just in the wash with darker branches, medium-sized roots and plenty of knees, and the red ones as islands with red branches. Note the long roots and some longer knees. You notice the spiky floor? Or did you know that trees had knees? No, well, the roots of trees breathe. they need to participate in gaseous exchange. So all that oxygen they spit out for us during the day, well, the roots need it back for respiration stuff. So if the ground is waterlogged, some trees can bend their roots up and access the fresh air. That's the tree's knees. If a tree falls over, but some roots stay attached, side branches can turn into trees themselves, all in a natural straight line. This is called a phoenix tree. And here we see some pollards or coppices. These are working trees. When you chop down certain trees at their base every 1 to 14 years for timber or fodder, then allow them to grow back before repeating this process, this is called coppicing. Pollards are done as part of agroforestry. No, this is not angry farming, quite the opposite. It's an alternative to modern farming. Imagine you want to coppice, but you have a cow or deer that nibble all the growth. Well, if you chop your trees at 3 to 4 meters, you can have your timber every 7 years without fear of nibblers, and you can chop the small branches every year for fodder and give them to cow. It is also worth noting that trees change shape as they get older. This can be caused by a response to many things: genetics, environmental factors, things like light, wind or pathogens. And when some trees are young, they'll be quite upright and monopodial, but as they get older may lose their apical dominance and become more forked and spready. For this video, we are mostly making the models as they appear in the pictures and not worrying about age and environmental factors affecting our tree's shape. But if you were making a type of woodland or a forest, it would be worth considering the trees' relationships with each other. How did I find out what trees to fit into each model? Well, books, Google Scholar, some old lecture notes I had. I also did a short course on the subject a long time ago. All the links I've used and any references are below. I'm sure there's plenty of mistakes in here or information that has changed since I acquired it. I hope that doesn't upset anyone. Please let me know so I can change it. I may make some more Minecraft videos if this one does well, maybe some realistic forest biomes, some woodland types based on IRL places, or maybe just some trees that aren't in Minecraft. If you have a problem with my walls looking a bit weird and you use planks on your trees, then go away, you rotten hypocrites. Goodbye. Thank you.